Well, we've already had some practice thinking about area and the relationship to integrals, because we've actually been doing this since we were talking about Riemann sums and estimating areas with rectangles. But I just wanted to quickly remind everybody that if I have some function and I'm looking to find the area from A to B of that function, when we write the definite integral, what we're really saying is I'm going to take some arbitrary cross section in here, and it's some kind of a rectangle. And when I go to find the area of that cross section, I'm going to have the height of the rectangle times the base. And when we were doing this with Riemann sums, we called our base delta x. And when we're doing it as an integral, we usually swap out that delta x and write it as a dx. So that's our base piece. The height we get from evaluating the function. So my height here is f of x. And then we add up all of the little rectangles that are in here. And an addition problem is a sum, and sum starts with s. And then we denote the fact that we're taking all of those little rectangles as far to the left as A and as far to the right as B. And that's how we write the notation for finding this area. In section 6.1, we're adding just one extra little piece to that, which is, well, what if I didn't have just a single function? What if I had multiple functions and I was trying to find the area between them? So I'm here to tell you, we've already been doing that. Here's what I mean. When we read this as the area under the curve, right? That's a phrase we've been throwing out there. But let's be real. This is not the area under the curve. If we were talking about the area under this curve, I would start shading it in. But all of this is also under the curve. What we mean when we say the area under the curve, we mean the area under the curve, but above the axis. Secretly, this formula to get this area could have looked like f of x minus 0. Well, no one's ever going to write that 0, but where that 0 comes from is that the equation for the x-axis is the equation y equals 0. Let's do something slightly more complicated. I can leave that up there. I'll leave that up there. Let's say that what I wanted to do was I'm going to have, how about, this is going to be y equals x squared. And that'll be the line y equals 6 minus x. I think that'll work out. And what I would like to find is the area in here. Well, if I take that same idea that really we're going to find an arbitrary cross section and then find the height of that cross section and multiply it by the base because it's going to be a rectangle. If I come in here and I draw in an arbitrary rectangle, to find the height of that rectangle, I'd be looking at the height of the function all the way at the top minus the height of the function all the way at the bottom. And I know this is my arbitrary rectangle, but just to kind of make this more concrete for a second, suppose that this was at x equals 1, and I wanted to know this height. Well, if I wanted to actually know that height, and I knew that it was x equals 1, then I would come and find this point, and that would be 1, comma, and then I'd be plugging it in here, 5 minus 1, 6 minus 1 is 5. And if I plugged 1 in over here, my x value would be 1, and 1 squared is also 1. So the height of that specific rectangle I would get by doing the 5 minus the 1. What we're doing with an integral is we're saying that at any given point, the height in here we would get by taking 6 minus x, the height of that top function, minus x squared, the height of the bottom function. Now there's one extra piece here that's making my problem slightly, it has one extra little twist. So I said that I wanted the area in here. So it's clear from my picture what the left-hand limit is, or the lower bound of the integral. But the right-hand bound of the integral, we're actually going to have to do some algebra to figure that out. So in general, if I'm trying to find the area between two curves, I'm going to have to figure out where those curves intersect. And finding intersection points means I'm going to set the two functions equal to each other. I am looking at x squared is equal to 6 minus x. And if I get everything on one side so that I can factor, I'd have x squared plus x minus 6 is equal to 0. And I think that factors, I try to make it factor. I think that's x plus 3 times x minus 2. So this looks like I've got two intersection points that they're going to intersect at x equals -3 and that they're going to intersect at x equals 2. And now I'm just kind of going to use my common sense and the fact that I have a picture to know that that must be x equals 2. And that x equals -3 would be if I extended this further that way, we can see that they would intersect over there. But the area that I shaded in would just go from 0 to 2. Once you have the integral set up, we're going to finish it off just like any other definite integral. We'll find the antiderivative and then plug in the endpoints. Just for practice, how about if you take 1 minute on your paper to turn this into a number by finding the antiderivative and plugging in the endpoint. So the first step here is we're going to find the antiderivative. The antiderivative of 6, I'm going to get 6x. And then when we find the antiderivative of x, we'll add 1 to that exponent and get x squared, and then divide by the new exponent. On the x squared, we'll add 1 to the exponent and divide by the new exponent. And that whole thing is going from 0 to 2. So when we plug in 2 times 6, that'll be 12. 2 squared is 4, and 4 divided by 2, I get 2. 2 cubed is 8, so I'd have 8 divided by 3. And when we plug in 0, all of the pieces will go to 0. I'll have 6 times 0, 0 squared, and 0 cubed. So we could leave it like this. We could do one little quick step to simplify and say 10 minus 8/3. When I'm graphing these to work on an area problem, I don't worry about making my graphs perfect. I know that this thing is some kind of decreasing exponential function. And I do know, and this one's probably worth knowing, that that +1 out there means that it should have a horizontal asymptote at 1. So this thing is going to look kind of like that. Now I mentioned that we're integrating on 0 to 4. So I am going to go ahead and take a minute to at least make sure that I'm pretty accurate on the 0 part. So when I plug in 0 for x, that's going to be e to the 0, which is 1. And 1 plus 1 is 2. So I don't need to, but I'm going to go ahead and label that 2 just to remind myself. And like I said, I don't worry about being super accurate on these. I just kind of need to know who's on top and who's on the bottom. Well, x minus 12, that's a line that's shifted down 12. So, and it has a positive slope. It's going to do something like that. My graph is not at all to scale. That's a +2. That's a -12 way down there, but I don't really care. When I changed my problem, I changed it so that I was 100% sure that this thing was definitely going to be lower than the other thing. Now, let's talk about this. This tells me that my X values are going from 0 to 4. Well, I know that when I plug in 0 for X here, I get negative 12. That's why I graphed it. And I know that when I plug in 0 here, I get 2. What happens when we plug in 4? Well, when I plug in 4 on X minus 12, I'm at negative 8. So I don't really know where the 4 is, but I'm going to put it somewhere over here because I know that at 4, my line should still be below the axis. Just to check, when I'm at 4, if I plug in 4 here, I don't know what e to the negative 12 is, but it's a really small number. So this is going to be some really small number plus 1. So that works out. This part of my picture looks pretty good. This is the area that we're going for. And like I said, if graphing isn't your jam, at least for right now, and certainly when you're working on the homework, I would go ahead and just pull up Desmos. If you're not sure about what those graphs look like, just throw them into Desmos. So this right here is the area that we're talking about. And the important thing in terms of setting up our integral, this is telling me that we're integrating from 0 to 4. I'm going to be subtracting my functions, and I need a dx. And really the thing that I need to know is which function is on top. Well, because I know what my picture looks like, I know my exponential is on top and my line is on the bottom. So when I put this in here, I maybe didn't leave myself quite enough space, but I'm going to have that exponential function minus my line. And if all I had to do was set this up, I could quit there. But I'm going to assume that we need to finish this off. Let's do this one together just to finish off. So I'm going to keep this from 0 to 4. I'm not ready to take the antiderivative yet. I'm actually going to go ahead and distribute the minus sign through and kind of simplify it first. So I've got e to the negative 3x plus 1 minus x. And minus a minus is going to make that plus. So all in, I've got a plus 13. The plus 1 from there and the plus 12 from over there. Now I'm going to take the antiderivative. I don't need to do a u substitution here because each of these pieces is separated by addition or subtraction. So we'll just treat each piece separately. Well, e to the negative 3x, this follows our rule that's showing up over and over again. And I'll maybe even squeeze it in the corner here, that if I take the integral of e to the kx dx, I get 1 over k e to the kx plus c. This shows up so often. I really encourage you to get this memorized, put it in that note sheet, something. So here, I'm going to get negative 1/3 e to the negative 3x minus x squared over 2 plus 13x. And we won't have a plus c because this is a definite integral. So I'm going to put in the 0 to 4. Now we're going to plug in the 4 and subtract off plugging in the 0. What we're not going to do is simplify our answer in any way. I'm just going to plug in the 4 and have negative 1/3. Oh wait, I lied. I'm going to simplify a little bit. Negative 3 times 4 is negative 12. I am going to write that as negative 12. 4 squared, okay, I can do that in my head. 4 squared is 16. 16 over 2 is 8. 4 times 13, probably someone more clever than me would do that quickly in their head. I'm not that cool. So I'm going to have all of that. This time, I do want to be careful plugging in the 0. We can still do it in our head if we want, but e to the 0 is 1, which means when we plug in 0, we're going to get negative 1/3 minus 0 plus 0. And I would walk away there. If I wanted to find, or if the question asked us to find the total area enclosed by these two graphs, this part of it, the cubic is on top. And in this part of it, the line is on top. So we would actually have to break this into two separate integrals to make sure that our value came out to be a positive number. I don't know if that maybe helps to clear things up. That's definitely a case where if you were to just assume that one of those functions was on top the whole way, that you wouldn't get the right answer. So if you're not sure, pop it in Desmos, figure out what the graphs look like, watch out for stuff like this. Based on that first test, I really genuinely do not think that Professor Chaudhary is trying to trick you. I think if there were going to be a function where this happened, I think he would give you the graph. Okay, onward to average value. And I asked you to find the average. I'm not asking for a number, but like, how do you find the average of these numbers? Anyone willing to unmute and say something or type it in the chat? Totally. You add them up and divide by the number of terms. That is how we find an average. We add them up and divide by, oh, I wrote a division bar. I probably don't need that part. Divide by the number of terms. Now, this changes a little bit when we're talking about the average value of a function, but that basic point, that basic underlying thing is still there, that we're going to add them up and divide by the number of terms. So let's say that I had the function, I'm going to keep my life pretty simple here, and I am going to call this y equals 3x squared. And I wanted to know, what is the average value for x between 1 and 7? Well, what does that even mean with a graph? So if I go to that idea of I'm going to add something up from, we're going to add things up. And in this case, we're going to be adding things up from 1 to 7. Well, adding things up calculus style says we're finding a sum. And finding a sum, we can write as an integral. So I'm finding the sum of each of the values. Well, each value of this function I get by taking 3 times whatever x coordinate we're at and squaring that. I'm going to add these up from 1 to 7 and then divide by the number of numbers in that interval. Now that one gets a little bit tricky. There are infinite numbers between 1 and 7, but that's getting too mathy for us. In terms of what we're doing here, I'm dividing by the width of the interval. I'm dividing by that entire time frame. So if I want the average value of this function, I'm going to evaluate that integral. Well, let's see. We can find the antiderivative of 3x squared. I gave us an easy function there. So the antiderivative is going to be x cubed. And we're going from 1 to 7. And then we would divide by how many things we had, or the width of my interval. So I'd have 7 cubed minus 1 cubed over 7 minus 1. I have no idea what 7 cubed is, but by the magic of my calculator, 7 cubed is 343. So this would be 343 minus a 1, 7 minus 1. I can do that one in my head, and I'm going to get 6. And 342 divided by 6 is 57. So that means if we go back to this kind of visually and a visual answer for that, well, for starters, when we're at 7, the height right here is 3 times 7 squared. I don't know what that is, so give me a second. 3 times 49, 147. So this right here is a height of 147. So this function has heights anywhere between, well, the height at 1 is 3. So in this interval, this function has all these heights between 3 and 147. But if we averaged all those heights together, we would get 57. The other way to think about this visually is this means that we took the total area under the curve, and then we divided it by the width. Well, if my area was supposed to be a height times, I don't even know what letter that's trying to be, a height times a width or the base. And if I took the area and divided by the width, right, we're going to get back to that average height. So if I were to draw in a rectangle with a height of 57, on that width from 1 to 7, then the area under this rectangle would be equal to the area under the curve on that interval from 1 to 7. What's the part you actually need in your notes? You are going to want this formula that the average value of f is equal to 1 over b minus a times the integral from a to b of f of x dx. We add them up and divide by the width of the interval. Have seen a lot of different calculus textbooks over the years, but this is the first textbook that I've seen that addresses the midpoint rule in this way. Remember how we had like right-hand endpoints, left-hand endpoints when we were approximating areas? Well, we also could have done midpoint rule with that. And that's really all the midpoint rule is. But our textbook puts a little spin on it. And in the section for midpoint rule, usually they don't give us a function. They give us a table or they give us a picture. But the idea is the same, that we're approximating something, we're approximating some kind of areas using rectangles. So I'm actually going to pull up the book because I couldn't make one of these problems. Well, I could make one of these problems up, but it'll be easier to just pull up the book. So I am going to look at, sorry, let me get zoomed in here. And I am, okay. So I'm going to share my screen for a second. So I am in the section that has the midpoint rule. And the one that I wanted to look at here is problem 20. So the width in meters of a kidney-shaped swimming pool were measured at 2-meter intervals as indicated in the figure we're going to use the midpoint rule to estimate the area of the pool. Okay, here's what I think. Okay, we're going to do this problem anyway. Here's what I think is kind of dumb about the midpoint problems in the book. If you were a scientist and you took measurements and then someone told you, oh yeah, we're only going to need to use half of those data points, that feels wrong to me. So if I had actually found all of these data points, I would not choose to use the midpoint rule because I'd be throwing out half of the data that I found. But to answer the problem, what we would need to do is to look at this and say, okay, we're going to use every other piece of data that we have because we're going to define those to be the midpoint of some rectangular slice. So I'm going to draw in a value of 0 on both sides that wasn't included for us. That's going to make 6.2 the midpoint of this interval to draw a rectangle around. That would make 6.8 the midpoint for my next interval, and 5.0 the midpoint of my next one, and 4.8 the measurement at the midpoint of my last rectangle. So even though someone took the time to find all that extra data, we're just going to use the values at the middle of the intervals. I'm going to stop sharing and stop my annotation here. But I did just want to point that out for a second. So the midpoint problems show up in 2 ways in the textbook. Some of the problems were given a table of values, and some of the problems were given a picture. We could be given a function, but that isn't usually how the midpoint problems are presented in this textbook. So if we were given a table of values, so let's say that we were given times and velocities. And we have velocities at 0, 1, 2, 3, 4, 5, and 6. And I am just making up numbers. So that's 10, 12, 15, 18, 29, 45, 60. And if I were asked to use the midpoint rule to estimate the distance traveled from t equals 0 to 6, then given these data points, I would say, well, I'm going to have to break this up somehow so that I have numbers that are in the middle. So if I broke this up, right, I don't have a data point at half a second. I only have these data points at, and actually, let me say that our velocity started at 0 just for no good reason. So my intervals are 1 second intervals, but I'm actually going to have to break this into 2 second intervals in order to have a midpoint. So I would break up from 0 to 2 and say that from 0 to 2, my velocity was 12. So I'd have 12 times 2 for my interval from 0 to 2. That got me to 2. Now I'm going to take the interval from 2 to 4. 3 would be the midpoint of that. So I'm going to use 18 as my velocity for the next interval. And then I'm going to have the interval from 4 to 6, and I'll use 5 to get my representative velocity for the interval from 4 to 6. So I'd have 45 times 2. I don't even know why we do this section. I think this is really dumb. Because if we had all of that data, we could use left-hand endpoints or right-hand endpoints. Or we could even use the trapezoid rule. But instead, the book is like, let's just throw out half the data points and not worry about them. It makes me very uncomfortable. And I've never seen the midpoint rule presented in this way in another textbook. Yay, midpoint rule. So I actually, I totally agree with you, Althea. I don't think the professor is going to like this either. And so it's possible he's going to present midpoint rule differently than how it was presented in the textbook. And if we're given a function, then I think midpoint rule makes sense. And we were actually doing this a little bit before when we were estimating areas. The reason that I think midpoint rule doesn't make sense the way it's presented in the book is because in the book, they're like giving you extra data and telling you to throw it out. But if we were just told to use the midpoint rule and we were given a velocity function, so let's say that I gave us a velocity function of, I don't know, 3 sine of t. And I wanted to use midpoints, not ponents, midpoints to estimate distance traveled from t equals 0 to 10 and have 5 intervals. This one doesn't bother me as much. This one doesn't feel like I'm throwing data out. This one is saving me the time and saying we're only going to look at 5 data points here. So this one goes back to very similar to what we were doing with the rectangles, where I'm just thinking about if I break this up from 0 to 10 into 5 pieces, then those would break up at 2, 4, 6, and 8. And then I would use the midpoint of each interval as the estimate for my velocity. So I would use t equals 1, t equals 3, t equals 5, t equals 7, and t equals 9. Keeping that the width of each interval is still a width of 2. So if we were given a function here, then working out this problem, since each of the intervals is 2, I'm just going to like factor that out to the front. So we'd have each interval of 2, and then we'd be looking at the velocity at 1 plus the velocity of 3 plus the velocity of 5, velocity of 7, and velocity of 9. Here we haven't wasted any effort by finding the midpoints. So this is how I've seen midpoint presented before in other textbooks. And